Yeah, I'm here from Busek. We cover a wide variety of propulsion systems for spacecraft, big and small. Today I'll focus primarily just on two of our electric propulsion systems for CubeSats. Probably just touch on the others a little bit. Busek is located in Natick, Massachusetts. It's just outside of Boston in the US. We are probably the largest staff, certainly in the US, dedicated solely to electric propulsion. We have over 50 people. I'll show, if there's time, a little bit about our facilities at the end of the talk. We historically have focused significantly on Hall thruster technology. We were the first US-built Hall thruster to go into space, and so far any Hall thruster that has been launched through the US has been either ours or based on licensed technology from Busek. We had the first micro PPT thruster in space, and most recently, this past year, the first successful electrospray thruster used in space, and I'll talk about that one a little bit today. And we've also been working with iodine propellant a lot in the recent years. I'll touch on that as well. In terms of missions, I mentioned the first US-built Hall thruster that was on TACSAT 2 from 2006. We had another of the same model of Hall thruster flying in 2010, the PPT 2007. And the LISA Pathfinder mission, which I'll talk about in a little bit more detail, launched in 2015, and this mission is actually ongoing still. In coming years, we've got two missions to 2018 here. These are scheduled to fly on EM-1, so it's looking like more like 2019 now. And we have ISAT as an iodine-based Hall thruster, scheduled to be ready for next year. And we have three electrospray thrusters to be delivered end of this year for flight next year. So in terms of CubeSat propulsion, we have a number of different systems covering different needs, different applications. The BIT-3, which I'm going to make it show and tell a little bit. This is the BIT-3 RF ion engine. It can run on iodine or on xenon, and I'll talk about it in quite a bit of detail. We also have electrospray thrusters. The BT-100 is sort of tens of micronewton class electrospray thruster. Pulse plasma thrusters. This is our micro PPT system. And we do have green monoprops. We have, in terms of the highest TRL level, a 0.5 Newton 1U system, which I have here with me if anyone wants to see it afterwards. But we also have developed thrusters at 0.1 Newton and up to larger levels up to 20 Newton. In the ongoing debate of what's a CubeSat, we also have larger systems, Hall thrusters that could be applicable to the higher CubeSats or small sat missions. So the BIT-3, as I mentioned, it's a RF ion thruster. This system is developed specifically, or has been developed for the two lunar missions to launch on EM-1. It has one of the highest total impulse levels that we're aware of in terms of impulse density. So the total impulse for a 2U system is over 35,000 Newton seconds, which, depending on your spacecraft size, gives you kilometer per second type delta V's, which I think we've seen lots of interesting ways you could apply that type of delta V. The thruster, like I mentioned, it's 1.6U, so it's a little smaller than 2U. 1.55 kilograms of propellant, solid iodine propellant, and 3 kilograms total. The thrust level is variable with input power, and ISP also varies along with that. So you can operate it down as low as 0.7 millimeters and up to about 1.25. In terms of power, the nominal power is around 70 watts, which we are seeing now is tends to be available. I think years ago this was a little more of a challenge, but in CubeSats now, as small as 6U, we're seeing these kind of power levels being available. The thruster is mounted on a 2-axis plus or minus 10 degree gimbal. If you're interested in that, I have a nice little video of it operating. The use of iodine propellant stored as a solid allows us to have a conformal tank that is at low pressure, which is for a number of reasons, obviously. The PPU is developed at Busek in-house. It's a radiation-tolerant design, we would call it, so it's a combination of COTS and rad-hard parts selected to meet the needs for deep space missions more so than TID type concerns in low orbits. And so I mentioned it uses iodine in the full system that we have developed. That's stored in a tank directly along the back of the 2U or 1.6U system. It can also run on xenon. This chart here just shows the thrust level on iodine and xenon. The performance ends up being very similar between the two. And we have developed and shown this on larger systems as well, up to 7 centimeters in size. The charts on the right, which are probably a little bit tough to read, just reflect the degree to which the performance in terms of thrust and specific impulse vary with power. So at lower power levels, you end up in this sort of 1500, 1400 second ISP range, and with thrust down around 0.7 millinewtons. And as you have more power available, you get thrust and specific impulse increasing, and that's a reflection of our essentially constant mass flow rate. So applications, the two missions end up being pretty similar. The system's going to be used by Moorhead State University's Lunar Ice Cube. We'll be looking for water and other volatile species in a low lunar orbit. So the thrusters are used to take that spacecraft and Luna HMAP for Arizona State University separately into a low lunar orbit from right off the SLS. In terms of status, we've recently gotten past our pre-CDR for those missions that's focused on the thrusters, so we are on target for delivery of those by the end of the year. So the TRL is rapidly increasing towards flight as soon as we can get them up there. Okay, so now I'll shift gears and focus on electrospray thrusters, which are probably a lesser known technology, I would expect. So electrospray thrusters, they take many different forms. The most simple, which is shown here, is a capillary type thruster where you have a propellant that's pushed or whipped through the capillary to the tip. You apply electric field to that, and you can snap the liquid into a sharp comb, which destabilizes and forms either a stream of droplets or, in some cases, a stream of ions. That distinction, the fact that we can design between droplets and ions, is one of the nice features of this technology, in that it provides a huge level of scalability, or adjustability rather, in specific impulse. If you operate in a purely droplet mode, you get very high thrust of powers of low specific impulse. Go to ionic mode, and you can get the opposite, high specific impulse and lower thrust of power. The LISA system was a case of the lower ISP range. And the focus of that was solely on high precision, getting the most precise, stable thrust we could possibly generate at the micronewton levels. And so the thruster specifically needed to hold proof mass inside this spacecraft. You didn't need to hold the proof mass, you need to hold the whole spacecraft in position about that proof mass to sort of nanometer scale. And it does that by providing thrust resolutions in the hundreds or less than 100 nanonewton levels. And that thrust noise is maintained at the 100 nanonewton level over very wide frequency bands, very, very stable. So this chart here just shows some data of steps of a couple hundred nanonewtons done during qualification testing for that program. So the thruster was actually completed and delivered in 2008 to Busek, and then didn't launch until 2015, which was worrisome. It was fully fueled the entire time. This was a new technology, so it was a big concern. But fortunately, everything worked well. All the 8 thrusters on board the flight have operated for more than 1,500 hours each. And the mission now has been slightly extended. So the full mission was a complete success, which is very exciting for a future potential full LISA mission where they would use this technology as part of a large interferometer to detect gravity waves, which is really exciting, really complementary to experiments like LIGO, if you're familiar, it's a different frequency band. But a neat extension that they've done now is to run the closed-loop algorithm to hold the spacecraft in place, but then monitor what happens when particles strike it. And the thrusters then react to hold position. And from that information, we can back out where these particles have come from, what their energy is, and where they hit the spacecraft. So they're calling it a comet crumb detector. So with that success, we're certainly hopeful that we'll be involved in the full LISA mission. Moving on from that LISA thruster, we've applied what I mentioned are some of the features in being able to move towards a higher specific impulse by emitting more ions and also miniaturizing technology. Higher specific impulse tends to happen at a lower flow rate, and you can get very low flow rates by removing the bulk majority of the feed system and instead using passive flow control through capillarity. So with that, we get small systems like this. Is the BT100 system. This nominally operates at thrust up to around 65 micronewtons, although you can go a little bit higher. And it has a thrust resolution at the micronewton scale. So the total power for this system is about 6 watts in the worst case, but typically even less than that. And like I mentioned, it has a capillary-based flow system, which is fully integral. So the entire flow system is inside this small cartridge here. We've developed a PPU, which is part of the integrated system, which all fits in about half a U. It accepts thrust commands directly and has a closed-loop control to provide accurate thrust. And we will have 3 of these modules flying on the NASA Ames Pathfinder Technology Demonstrator missions. We'll be delivering those at the end of this year. So electrosprays can be scaled quite immensely. As a demonstration of that, I'm just showing here. This is a relatively low TRL thruster, but where we've taken a similar technology, so there's a strip emitter here, and multiplexed it. And with that, we can get up to about 300 micronewtons at less than 6 watts of input power to the thruster head. So it's a quite high power thrust to power ratio from a small compact module. So this is about 5 centimeters, and it actually could be a little bit smaller than that. So with those kind of systems, we can start thinking about modularizing and placing these small thruster heads throughout the spacecraft, and you can do a lot of interesting attitude control and different maneuvers like that. The important thing to mention too, is relevant to that, is that it not only gets to 300 micronewtons, but it starts from a very, very low level, and that's really important. The degree to which we can throttle down allows us to meet both the low thrust needs and also higher thrust, which you might use for example, fast slew rates. So just going into a little bit more detail on the ACS type applications. If you were to compare a distributed system of these electrospray thrusters to something like reaction wheels, the benefits are that there are now no moving parts. So that little cube on the previous slide contains the entire propellant feed system. There are no valves or anything like that. So when you convert that to a torque resolution, it's significantly higher than, or smaller steps than you can get with most state-of-the-art reaction wheels. And most importantly, we can eliminate jitter. So there's no mechanical vibration anymore. So if you're looking for a very, very stable platform, this is a nice solution. So just an example of what you could do with something like that, if you wanted to look for asteroids or stare at stars in a situation where you need to have very, very long exposures without any jitter. So an example, you could point your spacecraft in an inertial stare at some bright stars and just gather light for seconds or minutes in a very, very stable manner, and then slew along without needing any reaction wheels at all, just using these thrusters. If you were to do that with something like a cold gas system, this is a 6U example, you would need a pretty substantial amount of propellant, whereas these modular electrosprays are much more compact. Final example, this is just kind of a fun little plot here. There are a lot of things you could do in terms of position control. I think you have many more ideas than us. Maintaining non-Keplerian orbits. This is an example of if you wanted to orbit around a spacecraft or other object in an out-of-plane circle. The thrust levels that we could produce in a continuous and throttled manner would allow you to do that in a very smooth and controlled way. So lots of neat applications, and I'd certainly like to hear from you if you have ideas. So I think I've mentioned most of the conclusions. I'll just skip really quickly to mentioning our facilities very fast. We have a very large facility with multiple high vacuum tanks, which we can test kilowatt level hull thrusters right down to these micromutant thrusters, which we assemble for the most part in-house in our clean room facilities. And just like to acknowledge all of our various customers and sponsors. Thank you.
We'll take any questions now.
Amazing systems. I have a quick question. When you mentioned the electrospray thrust, you have a multiplicity is less than 6.1. But is that the power is per unit? You need a multiple of the unit to maintain.
Yeah, if you want to use it for attitude control, you would need multiples of those. Yeah. But you don't necessarily need to have them all at 6.1.
I really appreciated the LISA presentation. That's really cool stuff. So I'm just wondering, like, the ELISA, it's a big question mark at the moment, but I'm just wondering, like, there's been studies how the mission would look like, and taking that into account, do you expect that you would use the same system that actually what you develop is good enough, or do you expect some next gen?
There will be necessary developments. The Pathfinder was really a technology demonstrator, so it's a higher risk. So a lot of the effort would be reducing risk and increasing reliability. But fundamentally, we would keep with the same technology. Okay.
Any further questions? No? In that case, let's thank our speaker.